Okay, good morning, good morning. Happy Thursday, welcome back. We start today on page 27 in the big packet, so open to page 27, please. And while you're doing that, we'll first have our look at the calendar. We just finished our 3 classes on statistical studies, capture, recapture, and clinical studies. So we looked a lot about samples and lots of vocabulary associated with all those things. And then the next 3 classes, kind of changing gears. We're going to talk today about counting, next class about probability, and then the next class after that is about chances. So the ultimate goal of these 3 classes is to be able to estimate or figure out probabilities of certain things happening. If you're watching a basketball game, what's the probability that this person hits the next 3 shots in a row, next free throws in a row? If you're playing the lottery, what's the probability you're going to win the top prize or one of the smaller prizes, right? You're more likely to win one of the smaller ones than the big multi-million thing, but what's the probability of that happening? Lucas? We're not going to learn how to count cards, but that is it's related. Yeah, but you can think about probabilities in craps and roulette and blackjack. So that's the goal of these next 3 classes. So one other note, what's happening on Tuesday in this class? Project is due. So project number 1 is due in 5 days. 5 days is a long time, so even if you haven't started the project, which I hope doesn't describe very many people in this room, there's still 5 days left to do it, so do it. And if you have questions, I'm happy to answer them. You can email me. If it's over the weekend, you can call me. But this thing is due on Tuesday, and if you don't hand it in Tuesday and you hand it in late, there are penalties, and we don't want to get into that. So you have time. I know that some folks have already turned in the completed project and gotten stuff done, but regardless of where you are in that process, it's 5 more days before this thing is due. Any questions about the project? Okay, and then one other announcement before we look at the new stuff for today, and that is, where'd it go? Here. You recognize the name of either of these gentlemen? Shapley. Have we not done something about Shapley? Remember the weighted voting systems? We had the first one was the Bonzoff Power Index and then the Shapley-Shubik Index. Just last week, the Nobel Peace Prize in Economics was awarded to these 2 gentlemen. So Lloyd Shapley, still alive and well, I think he's about 90 years old, was one of the co-winners of the Nobel Prize in Economics. It talks a little bit about what he did, the theory of stable allocations and the practice of market design. That's what he was awarded the prize for. Okay, let's come back here. Again, we are on page 27. So we'll go back up and start at number 1. Can we go to Kristen? Actually, we'll go to Laura first. Number 1, please. Okay, so let's look at a few examples of a random experiment, just something where you can't know beforehand what's going to happen. If you flip a coin, you're not going to know whether it's going to be heads or tails. It's random. If you roll a die, random. If you just guess on all the answers to a multiple choice test, you are performing a random experiment. You don't know whether or not you're going to get them right because you're just guessing. And then whether or not you get stopped at a traffic light, the one at Main and Federal, random. Right? Just depends on when you get there and the traffic flow and the patterns and all that, but you can't know ahead of time what's going to happen. So all those things are random experiments. Kristen, are you ready? 2, or B, actually. Okay, so if we wanted to list all the possibilities for flipping a coin, what might happen? What could you get? Heads or tails? So heads or tails, where is it? Here is the sample space for flipping a coin. So the sample space is just the word that describes list all the possible outcomes. List everything that could happen. How about if you roll a single die? What are the possibilities for what you get? 1, 2, 3, 4, all the way out of 6. Some people are saying 1 in 6, which is a probability answer, so we're going to get there next class. If you wanted to know the probability that you get, for example, a 3, it's 1 out of 6. So we'll get there next time. But right now we're just listing the possibilities. And what if you guess on a multiple choice test? Well, the sample space is the set of all ways you can do that. And that could be a very big list, right? And I'm not going to write it out. It's just all the possible ways to answer all the questions on this test. And then finally, what are the possibilities for that traffic light? Traffic light has 3 states. green, yellow, and red. Those are the, that's the sample space. And so if we're thinking probability, and it's equally likely that it's green, yellow, or red, then you have a 1 in 3 chance of hitting that when it's green. Do you think it's equally likely that it's green, yellow, red? Which one of those is definitely the shortest time? Yeah, like yellow is the short. I don't know whether green beats red or whatever, but I know yellow is definitely shorter than the other two. So unfortunately, this one, it wouldn't be as easy as 1 out of 3 because the chance that it's yellow is much smaller than the chance that it's green or red. If you are at an intersection and you're on the less traveled road, like if there are two roads intersecting and one of them has hardly any traffic, what color do you think that light is most of the time? Hopefully it's red, right? You've been at these roads where you're just not on the main road and you're going to be red for a while and all the main traffic gets to go green for a long time and then once in a while you get your green. So it's not always as simple as a 1 out of 3 or 1 out of 2 or 1 out of 6, just because things aren't always equally likely. All right, let's go to number 2. Danny, are you ready? Okay, so the goal is to be able to count how many things are in a sample space. So when you flip a coin, how many outcomes are in that sample space? 2. You can get heads, you can get tails. When you roll a die, how many outcomes are there? There are 6. But for a lot of the questions we're going to answer, the number of outcomes is going to be a whole lot harder to count than these 2 things. And there are going to be so many possibilities that we're not going to want to list them all. We're going to want some technique for counting. So if I said, for example, there is I'm going to give you guys a true-false test. It's going to be 10 questions on it. And I want to know how many different ways you could answer all the questions on the true-false test. So one way would be to say true, 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 all the way to the end. That's one way to answer, right? Another one would be true, 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 and then false on the last one. Or we could do false, true, true, false, false, true, false, false, true, true, true. There are a lot of possibilities, right? We're not going to want to list all these combinations of T's and F's. So the ultimate goal for us is to just be able to count when listing them is not necessarily feasible. So let's look at this next possibility here. We'll go to Stephanie for how many? Okay, we're going to flip a coin first, and then we're going to roll a die. And the question is, how many ways can that happen? Now, some of you might already know the answer for how many ways that can happen if you flip a coin and roll the die. But even if we don't, we're going to list them, and that's going to give us a general idea. So if you flip a coin, what could you get? Heads or tails, right? So suppose that we get heads on the coin, and then you roll the die. What could you get? Could you get a 1? That seems like a natural place to start. Let's keep the heads there. What else could you get on the die? You can get a 2, and we're going to list them all. Can you guys list the rest of them? So keep heads for as long as you can, and then once you've run out of all the possibilities where you got heads, then make it tails, and keep it tails the rest of the way. But try to list them in some organized way, some orderly way. So you can have heads 1 through 6, or tails 1 through 6. Yes? One of them is a Schwarzenegger movie. Nothing? Nothing? One person gets, 2 people get what I'm talking about? Yeah. Did we not call it T2? Oh, you guys are way too young. So how many possibilities if you just flip a coin and roll a die? You see 12. You listed 12 things. So there are 12 possibilities here. But what if we don't want to count them all out? Like, what if we don't want to list them all out? Like, instead of 1 coin, there were a dozen coins. And instead of 1 die, there were 10 different dice. So let's come up with some way. Why was it 12 in this case? Can you say something about flipping a coin and rolling a die that naturally leads us to the number 12? Lucas? Lucas says we multiply. 2 outcomes for the coin, 6 outcomes for the die, Multiply them, we get 12. Do we believe this works, or was this just a coincidence of these numbers? Does it seem reasonable? Yeah, this is one of these. This is a general rule that's actually going to be the most important counting thing for us. We're going to talk about a lot of different ways to count. That's the most important thing right there. Is that if you're doing one experiment followed by another one, you multiply the number of ways there are to do each one. So that's written out here in number 3. We'll go to Mike. That's it. If you have one experiment followed by another, what you're going to do is treat them completely separate, count how many ways to do each one separate, and then multiply your answers when you come back. So let's see if we can do number 4 together. Yeah, Tim.
I just have a question. So say you have 2 dice.
Yes.
So you still have the 1 point.
Yes.
Roll numbers 2 through 12. Can't roll.
Okay.
So that's
It's a good question. So Tim is asking us, so Tim says that we have the possibilities 2 through 11 when you add up 2 dice. Do we believe that? Sorry, 2 through 12. 2 through 12. So if we add the numbers on 2 dice, you guys buy that the smallest thing you could get total would be a 2 if you got a 1 and a 1, and the biggest thing would be 6 and 6 is 12. So it feels like, let's see, the numbers 2 through 12, there are actually 11 numbers in that list. So does the 11 somehow come into play? And I'm telling you the answer is no, because there's no 11 in coins or dice, like a single die is 6. But it's because when we try to decide what the outcome is, we're not saying what's the total on the dice, we're saying what is the outcome. And so, for example, one possibility for Tim's experiment here could be I get tails on the coin, I get a 3 on the first die, and a 1 on the second die. And I'm not combining them and making that a 4 and just looking at a total of 4, even though for a lot of games you roll the dice and then you add them up. That's not what we're doing. We're looking at the outcome that happens. T3 and 1 is one possibility. T2 and 2 is a completely separate and distinguishable possibility, right? If I just showed you these two things, like actually on coins and dice, you would know they were different, yes? So even though adding is a natural thing to do with dice, that's not what we're doing here. We're just counting possibilities. Let me ask you one more. T13, same or different as T31? Could you tell them apart? That's the question right there. What color are the dice you guys are all picturing right now? They're all white, right? Or they're probably the same, whatever they are, they're probably the same color. I'm guessing they're white dice. Okay, but there's no restriction says the dice have to be the same color, and if they're the same color, you can't tell them apart. But if the first die is blue and the second die is black, can you tell the difference between a 3 on the blue and a 1 on the blue? We can tell them apart, right? So sure, most dice games to play with, you can't because you don't care. You're just adding them up. But these things happen in an order, and we can tell the difference between a 1-3 and a 3-1. All right, so let's see if we can extend Tim's example and make it even tougher and answer part A here. So it says, how many outcomes are there for each of these experiments? So we're just going to count. We're going to roll 2 dice, and we're going to flip 5 coins. 2 dice followed by 5 coins. Now there are going to be some shortcuts, and maybe some of you are already heading there, but I'd encourage you to just write out a few calculations before you think about any shortcuts. 2 dice. Let's look at the first die. How many possibilities for the first die? 6. How many possibilities for the second die? Also 6. For the first coin, how many possibilities? 2. For the second coin, 2. Third coin, fourth coin, and fifth coin. I've written down all of these numbers. There's 7 numbers up there because I had 2 dice, 5 coins. So I've got 7 things happening, 7 numbers. According to this fundamental rule, what should I do with those numbers? I should multiply them. Something enormous there. I'm going to multiply all this stuff together. And Mariah says it's 576. All those outcomes are different. All 576 of them are different. Just like T31 and T13 are different. There's no duplications in those 576. Okay, so we are going to talk about things where the order does not matter. But for me, I've got a red die or a blue die and a black die, and I can tell they're distinguishable. Every die is different, and even let's make the coins different. Let's make the first one a penny, the second one a nickel, right? We just make them all different. We will talk about things where the order does not matter, and that's one of the questions we'll have to ask with every problem is, does the order matter? These are all distinct objects. We're just multiplying them straight across. We don't have to divide by anything. Morgan. So it should be 1. Thank you. Okay, updated. So 1,152 possibilities for rolling 2 dice and flipping 5 coins. That's a lot. I don't want to list them all, but I can tell you exactly there are 1,152 ways for this experiment to come out. One other thing, I had said there were some shortcuts. Instead of multiplying 2 by itself a bunch of times, what's the shorthand version of writing this number? That's 2 to the 5th, yes? What is this? 6 times 6 is really 6 squared. So you could look at that question and maybe right away think, oh, it's just going to be 6 squared times 2 to the 5th. But it's really dangerous. I think that instead of doing 6 squared, some people might be tempted to do 6 times 2. Instead of 6 squared, be 6 times 2. So I would encourage you not to try to go for these kind of power shortcuts and just write them out. Write out a slot for each of the different experiments you're performing. Let's try part B. We're going to go to our favorite restaurant. We're going to pick a meal. And the choices we have in front of us, there are 5 different appetizers, there are 8 entrees, and then there are 5 different desserts at the end. So do we kind of feel that this is 3 experiments back to back to back? How many possibilities for the first experiment? 5. You're going to pick 1 of 5 appetizers, anything you want. And then how many possibilities for the entrees? 8, and then there's 5 desserts. And what do we do with these 3 numbers to find how many different meals we could concoct? You multiply them, right? For each appetizer, you could have had any of those entrees, and for each of those meals, you could have had any of these 5 desserts. So altogether, we get 200. So you could go to your favorite restaurant every night for more than half the year and order something different. Each one of those combinations is different. Lucas. Yeah, so if there were restrictions, then maybe we'd have to think more carefully. But in this case, without any restrictions, we just multiply all those numbers together. There was an advertisement, I don't know if it's still on TV, but I've seen it pretty recently for Olive Garden, and they have this kind of all-you-can-eat pasta special that they were running, maybe they still are. And I don't remember the exact numbers, but it was something like, I don't know, like 6 different kinds of pastas, and 5 different kinds of sauce. And then the next line is the possibilities are endless. So I debate that claim. How many possibilities are there if you have 6 pastas and 5 sauces? 30. There are 30 different possibilities. You can get the spaghetti with the marinara sauce, or we could go with the bow ties with the Alfredo sauce. There are 30, which is a far cry from endless. I was going to write a nasty letter, but I didn't get around to it. So let's go to the next page. Filling out an answer sheet for a test with 3 true-false questions and 10 multiple choice. And the multiple choices have 4 choices each. So you've got this big test. The question is, how many different ways could we answer all these questions? So let's just split this guy up. How many possibilities for the first question, which is a true-false? There are 2 possibilities, true or false. How about for the next true-false question? There's 2 choices there, and then 1 more true-false question has 2. And then we get to the multiple choice questions. So how many options do you have for that first multiple choice question? is 4, according to the directions here. It says 4 choices each. And what's the next number? Is a 4. And the next number is a 4. I'm just going to put ... but I feel like we're ready to kind of jump to the answer here. What are we going to do with all these numbers once we've got them written? Is we're just going to multiply them. And so I said avoid the shortcuts. Okay, sure, but I'm lazy and I don't feel like writing all these 4s out. But can we maybe kind of come to the conclusion so we can type it on the calculator easier? So what do we do with all those 2s? 2 to the 3rd, and then 4 times 4 times 4 times 4 is what? 4 to the 10. Yeah? All right, actually I'll make a guess for what this enormous number is, but do we buy that this is the thing we're trying to find? And I'm trying to, again, encourage you not to just jump to these shortcuts. It's really easy to say, oh, I have 3 true-false questions, and each of them has 2 possibilities, right? And so we multiply and we get 6. You don't get to say 3 true-false questions. It's separate every experiment. So the first question is one experiment. The second question is another experiment. So it's not multiplying the number of questions by the number of choices. It's multiplying how many choices you have for the first question by how many you have for the second question, by how many you have for the third, okay? It's really easy to make this mistake. So I'd encourage you just write out a number for each question. Those are the things we multiply. Okay, so this is going to be something like, let's see, something like 8.5 million. Yes? Is nobody impressed that I just estimated 8? Come on, that's pretty good. That's pretty good. All right, let's go to part D, and this one is about horses. So making a wager for the top 3 horses in order of the Kentucky Derby if there are 10 horses in the race. And first we'll find out who our gamblers are in this room. Anybody know the name of that particular wager? No, it's not that. It's not a math word. It's a horse racing word. No? All right. So this one is called the trifecta. We've heard that before. Gina's got it. Well done. So the trifecta, 3. So if you go out there and you say the top 3 horses are going to be this horse, then that horse, then that horse, and you win, you're going to win a lot of money. But the likelihood of you winning is pretty small, right? Because you got to get the top 3 in order. But let's go ahead and find out how many possibilities there are. So let's just look at the first horse to finish. How many options are there to pick a winner of this race? There are 10. There are 10 horses total. That's going to be our first horse. Once that horse has crossed the finish line, how many horses are still left over to maybe finish second in this race? There are 9 horses. Because the one horse has already won the race, and they're not going to come in second place after they've already finished the race in first. And once the first and second place positions have been established, how many choices for the third place? There's 8. And then we stop. In this game, in this bet, you don't care who finishes 4th or 5th or anything else. So don't go all the way down, because we weren't looking at all 10 horses finishing, just the top 3. What should we do with these 3 numbers? Let's multiply them. So 720 different ways that these horses could finish. All right, so again, most important thing for today is multiply. List the possibilities for each experiment. Just write them out, even if it feels like it's a little bit of a pain, like in the previous example, just write them out, multiply. You won't go wrong. All right, let's go to, is there a question, Danny? I thought you had your hand raised. Okay, can we go to Shawnee for number 5? Okay, so we're going to talk about that horse race example again. Suppose you have a group of n objects and you want to pick r of them. So we're making this real general leap here from the specific numbers to general. I will show you. Well, let's get there first. So n objects, and you're going to pick r of them. What were the n and r for the horse example? How many objects did you have to choose from for the horse example? Yeah, we had 10. So in our case, n was 10. And how many of them were we actually picking to care about? Was just the 3, okay? So you had 10 objects, 10 horses to choose from, and you were picking 3 of them, the top 3. For what it's worth, n is always the bigger number. If you need a shortcut, n is the bigger number and r is the smaller one. And then we're going to have this little technical detail. It says here, further suppose each object can only be chosen once, and that the order in which they're chosen matters. Each object can only be chosen once. So once you've chosen your winner of the race, are you going to pick them again as your second place? No. So we only choose a horse once, and the order in which they're chosen matters. Yeah, I mean, it's a horse race. If your horse finishes first and somebody else finishes second, that is different from your horse finishing second and the other guy finishing first. So the order matters. If all of those things are true, then we use the word permutation. Permutation. So there's a formula, which I'm not going to ask you to memorize or use. I'm just putting it here to show you that it exists. But the formula for the number of ways to pick r objects out of n of them is given by n factorial over n minus r factorial. In our example, how much was n again? Was 10. So there's a 10 factorial over, how much is, let's see, so there's an n down there. That's also 10. How much is r? It's 3. So using that formula, which you shouldn't be clear on where that formula is even coming from, but we get these numbers for the horse race. Okay, 10 factorial divided by, inside the parentheses is 7. So it's really a 10 factorial over 7 factorial. And I'll type that into our calculator and just see if we get the 720 that we were talking about before. So on this calculator, it's 10 and then inside of math, and then the left arrow gets us over to probability, and then the 4 is the exclamation point, the factorial, and then divided by 7, and then we go back in there. And again, the answer to the horse question was 720. And if I've done that correctly, we get 720. I'm going to walk around when you guys are working on the group activity today and make sure everybody's able to do stuff with the calculator, but I don't want to interrupt the flow of what we're doing now. So if you can do this, fine. If not, I'll come to your table each individually in a little bit. Yeah, you can just go right to 7. I just wanted to show it in detail one time. And then actually the other thing we can do for this example is just write this in symbols. So again, our n was 10, and then there's this big P, and then there's the R, which is 3. And 10P3 is also something I can do on my calculator. And so on this calculator, and yours might be a little different, I'll fix it later, we would do 10. And then inside of one of these crazy submenus, the same place we found the exclamation point, what else do you see? You see an NPR. It doesn't stand for National Public Radio, it stands for permutations. All right, so NPR is that formula. The calculator knows it. So I'm just going to go down here to number 2 and select it. Do you know what else it's waiting for? What was I trying to type in? I wanted 10P3. So it's waiting for me to type the 3. And so if I just type that, 10P3, it should give me the same 720 that we got. It's kind of nice. It's built in. You don't have to do the multiplication out. You don't have to do the factorials out. You just have to know, oh, it's a permutation, and my calculator can handle the details. Good. Okay, again, I'll come around and answer calculator questions in a little while. So let's go to number 7, and can we go to Patty? Okay, so let's think about this one. So the first card that's going to get picked, how many choices are there? There's 78 cards available. Any of them could be the first one that gets flipped over. And then once you have already flipped over that card, we don't put it back in the deck. So how many choices are there for the second card? 77. And then 76. And as Patty read, we want 10 cards total. Can you guys figure out what the last number is in this list? I'm just going to put a dot, dot, dot. We're doing 10 cards total. Those are the first 3 of them. So what's the last number in this list? Is it 68? It's not 68. If I want to list 10 numbers, starting at 78, it feels like the last number should be 68 because that's 10 away. But actually, if you count each of these numbers in the list, and I haven't written them all, you'll actually find there are 11 numbers in that list. So it's really deceptive. This idea of just subtracting does tend to mislead. So that's one reason that writing it all out can be a little bit tricky, is that you might stop at the wrong number. But the more important thing here is that it would be really annoying to have to type this thing into the calculator. 78 times 77 times 76 times 75, all the way down to 69. It's just annoying. It's not hard, it's annoying. So what should we do? Well, let's use our the new tool that we just learned about here. This is a permutation because you're never going to pick the same card twice, right? As soon as you see one card, you won't see it again. And the order in which it comes out matters. So if you get the black skull first and then the happy squirrel second, it's different from the happy squirrel and then the black skull, right? Different outcomes, different readings. So this is a permutation. The big number goes first. How many cards did we have to choose from? 78. How many cards did we actually want to choose? It was 10. So this answer, multiplying those things out, which is annoying to type in, is the same as 78p10. And that's not so annoying to type in when you know how to do it. It is a big number. So 78p10, of course it's going to be big. 78 times 77 times 76, all the way down to 69. And we get that. You guys remember this E18 business? What does E18 mean? What does it mean? It is scientific notation. So it means it's 4.5 times 18 times 10 to the 18, or equivalently 18 places. Take that decimal point right there, move it over. 1, 2, 3, 4, 5, 6, 7, 8. Keep going. You got to move it 18 places. So it's probably not all zeros. It's just the calculator doesn't have enough room to show me what it really is. But anyway, it's an enormous number. So I'll just write it here. It's about 4.566 times 10 to the 18. That's a lot of different readings. But that's how many readings there are, how many possible outcomes of flipping over 10 random cards from this tarot deck. Okay, so now we're going to come to something Lucas had mentioned. We'll go to 8, and I think we're up to Gina. Okay, so far everything we looked at today, the order matters. So for example, when you're making your guesses on my true-false test, is answering true on the first one and false on the second question same or different from answering false on the first and true on the second? It's different, right? It's actually the complete opposite of what your first guess was. So the order in which you put down these T's and F's makes a difference. What about the horse race? If you say Secretariat and then Man of War, first and second, same or different from Man of War and then Secretariat? It's different. So the order in which you write down your horse names matters. What about rolling the dice? Well, we had to talk about it really, but if you can tell those dice apart, if one is black and the other is blue, then can you tell the difference between getting a 3 on the first and a 1 on the second from a 1 and a 3? Yeah, we can tell the difference. So the order in which every experiment we've looked at so far, the order mattered. So if we don't care about the order, it's actually called a combination. There's a formula. It looks quite similar to the permutations formula. I'm also not going to ask you to use it or memorize it. I'm just going to point out that the calculator knows that formula and we're going to use it. So let's try number 9 here. We'll go back to Morgan. Okay, so we're going to have 2 races. I'm just going to run to determine who makes it to the finals. How many horses are going to make it to the finals? 3. 3 horses are going to advance past that first round and they'll make it to the finals. But the order in which those first 3 horses finish in the first race doesn't make any difference. All you got to do is qualify. I watched a lot of Olympics this summer, and in all these heats, like track and field and swimming and gymnastics, all the heats, it didn't matter what order you finished. Everything gets wiped off the books when you get to the finals, but you just got to get to the finals. So make it to the top 3 or make it to the top 10. You just got to make it. You don't care where you finish, right? All the data is erased. Same kind of idea here. Just make it to the top 3. So then can you guys tell me, if all we care about is who the top 3 is the following, are the following outcomes the same or different? Man of War first, Secretariat second, Secretariat first, Man of War second. It doesn't matter. It's exactly the same outcome if all we care about is who the horses are and not in what order they finish. Either way, I can tell you that both of those horses have qualified, and that's all we're after here. So if the order doesn't matter, then we need a different formula. It's this combination thing. And that's what Lucas was talking about with the division. So let's see. So it says the order in which they finish is irrelevant. That phrase right there is our tip-off that says use combinations. Use combinations. Okay, so we're going to have a big C. How many horses do you have to choose from in this race? You have 10. And how many of them are we choosing to make it to the finals? Just 3. So this is 10C3. And that's equal to 120. I'll just show it just for the purposes of this video. If you happen to have this calculator, here's how you type that in. So we type in the 10, we go back into math and go to probability up here, and then NCR is right below NPR. So we just scroll down or hit number 3. And then we get 120. So 120 different possibilities for who advances to the finals. Okay. Let's come down here to number 10. We'll kind of summarize with Alex. Yeah, the long way is to use this formula. Upstairs goes n factorial. How much is n? 10. So it's a 10 factorial divided by r factorial. How much is r? 3 factorial. And then n minus r is 10 minus 3. You could just write 7 if you want. So that's the long way. Okay, we'll go to Alex for 10. Okay, before we flip, let's stay here for just a moment because that's really important. Right now, we have 3 ways to count things. Those are going to be the entire number of ways we'll learn to count things. We've seen all the different possibilities for us counting things. It's 3 ways. The first way was multiplication rule. Second way was permutations. Third way was combinations. So, all right, it's not so exciting to ask the calculator to do the calculations. That part's boring, but you got to ask the calculator the right thing if you want to get the right number as the output. So a big part of what I'm going to be looking for on our upcoming test is picking the right choice, make the right choice. Once you've made the choice, it's usually pretty straightforward to actually get the number out of the calculator. So first question, we're going to go through this kind of flowchart thing, and it's actually on one of the pages at the start of this packet. But what you have to ask yourself first is, are you allowed to pick the same thing twice? Could we pick the same horse twice? No horse will finish first and second. Could we pick the same tarot card twice? No, you're going to have unless you put the card back in the deck, you'll never see the same card again, you know, once you flipped it over the first time. But in this case, but in the case of like the true-false questions, are you allowed to pick the same thing twice? Can you say true and then later on say true? Yes. So sometimes you can pick the same thing again, and sometimes you can't. And that's the first question we have to ask. So let's just take a quick look at, I think it's going to be page, maybe it's page something. Somebody find this for me. 1, 2, here it goes. So page 5? Page 5. So on page 5, there's this flow chart. We're going to run through it together, and I'd encourage you to have this handy when you're doing your homework over the weekend and tonight. And the flowchart is supposed to help you decide which of the three counting methods you use. Are you going to use the multiplication rule, or permutations, or combinations? And so here's our way of deciding which one to use. And just one note, you are going to bring this with you to the test. So you'll have this in front of you when you come to the test. Just rip it off on the day of the test. Right, so you make your own cheat sheet with whatever you want, plus this. Okay. All right, so the first question is, are the objects all different from each other? The dice, were all the dice different from each other? Yeah, we made them different colors to really know that we could tell the difference between them. Are the horses different from each other? Yeah, in fact, every question that we're going to talk about, the answer is going to be yes. I mean, it could be a no, but in this class we don't cover it. Things can get kind of complicated pretty quick if the answer is no. So for example, I'll just give you a real quick question that we're not going to tackle, but where the objects are not different from each other. Suppose that I have 5 cookies. So here are my 5 cookies. Pretend that they are all exactly the same. They're all chocolate chip and they are not distinguishable from each other. Okay? So here's the question. I've got Grace and I've got Mariah here in front of me, and I'm going to divvy up these cookies. Now, I'm not going to split any of the cookies. So is this going to be fair no matter how I do this? No. So here's the question. How many ways could I split up these cookies to Mariah and Grace? So if I really think Mariah is having a good day, what might I do? Could do 3. You guys are being fairer than you need to be. We could give her all 5. Grace gets nothing. Okay, that's one possibility. Or we could say, okay, we'll throw Grace a bone, we'll give her 1, and Mariah can have the other 4. Or it could be 3 and 2, or 2 and 3, or 1 and 4, or 0 and 5. So a bunch of different ways to divvy up these coins. If I bring Tim into the mix, now it's quite complicated, right? I could give 2 and 1 and 2, or 3 and 2 and 0. There's a lot of possibilities, but the idea here is that I can't tell these cookies apart as part of the setup. So are the objects different? No, they're all the same. And so in this case, it would be kind of complicated. We're not going to talk about it, but that's the kind of question where the objects are different. So sure, you should ask that question, but the fact of the matter is, in this course, there's no need because the answer will always be yes. So we'll just skip to the next question. It says, can the same object be chosen more than once? So for the horses, can you choose the same horse more than once? No. Can we choose the same tarot card more than once? No. So we'll kind of put this branch over here just to remind us, and feel free to write, you can write whatever you want on this piece of paper. You'll bring it to the test, and I trust you can write anything you want, like horses and tarot cards. And so if the answer is no, you're never going to choose the same object more than once, then you have another follow-up question. You say, okay, does the order matter? For the tarot cards, does the order matter? Yeah, the happy squirrel and the skull, different reading than the skull and the happy squirrel. So so if the order matters, it is a permutation. Use a permutation. You found your decision. If the order doesn't matter, like for the horse race where we just looked at the top 3 and we didn't care about who finished first, second, or third, we just wanted to qualify for the finals. If the order doesn't matter, you use combinations. That's what you have to do. There's no choice. So that's the one branch. The other branch, actually going to be even a little easier. If the, where are we now here? So this was the branch where you can choose the same object more than once. For example, on a true-false test, you can choose true several times. What if I'm just trying to figure out how many different possible telephone numbers there are? Do any of you guys have a telephone number where you use the same digit more than once? Yes, so could you use the same object more than once for telephone numbers? Sure. So we'll put that as another example here, so phone numbers. Does the order in which the objects are chosen matter? What about the true-false test? Does it matter whether you do true and then false, or false and then true? Those are the same. If I give you a test and one of you puts true, false, and the other puts false, true, you're going to get the same grade? No, that's totally different. So the order makes a difference for true-false test. What if I swap a couple of digits in your phone number? Does that matter? Yes. Totally matters. So the order makes a difference for phone numbers. So if the order makes a difference, you use the multiplication rule. And that was the first few examples that we talked about, where we had the true-false test and we had the rolling the dice and flipping the coins. We used the multiplication rule. If the answer is no, it's something called a combination with repetition. We're not going to cover those today, so this branch gets easier by virtue of us not looking at those kinds of problems. Lucas.
A phone number, wouldn't that be more complicated? Normally, phone numbers are set by a certain numbers, when the sequence order, area code, and let's say for the group there, it's 77, then the last 5.
That's right. So if I just wanted Greenfield phone numbers, and if everybody in Greenfield has a number that starts 77, then actually I've lost some freedom. I can't just pick anything in those first 2 slots. So then you'd only have 5 digits to play with. But still, we could use this kind of idea where you just say, just start with the last 5 digits. That's the only thing yeah, the permanent ones are already in there. There's only one possibility for each of them. They're both 7. And then we just pick up with the parts that we actually have some choice with. Good. All right, so here's how we're going to do this. Can we jump? We'll just do a few problems together, and then you guys will do a bunch on your own. But we're back to page 29. And we're going to go to Greg for 11. Okay, good. Let's go to Tim for A. Okay, so we have a lot of different dodgeball teams we could make from you folks. 6 people on a team, and the question is, how many different teams are there? Okay, so we're just going to get a few people out of their chairs. Can people at this table right here stand up, please? These 3 people stand up here, and Shawnee, can you stand up? Okay, this is one team. Yes? I'm actually kind of intimidated by this team. All right, that's one team. They look tough. Okay, Shawnee, have a seat. Everybody else stay standing. Gina, could you stand? Is this a new team or the same team? Completely new team. Right, completely new. Okay, let's get Mike to sit down. Patty, can you stand up? Same or different right here? Different. Okay, everybody sit down. Do you guys buy there are a ton of different teams we could make from the people in this room? I don't want to list them all. We really don't. So let's see if we can follow our flow chart. You can open it if you want. I will remind you the first question that we're going to ask is, because we crossed off the one at the top, we're never going to ask that because it's always going to be yes. So the first of 2 questions that we ask is, are we allowed to choose the same object twice? So that's the first question. Can choose same object twice? So if I say Laura is going to be on my team, and then Mike is going to be on my team, and then Laura is going to be on my team, that's no good. So we're not going to choose Laura twice. So the answer to this one is a no. No, can we choose the same object twice? And then we're going to ask about the order. So does the order matter? So you're not going to choose the same person to be on your team twice. You got to choose 6 different people. Yeah. Does the order matter? This is oftentimes a very hard question to answer. So here's how I answer it, because it's not always clear. I say, okay, Laura, can you stand up, please? Laura is on my team. And then Kristen, can you stand up? No? Okay, here are 2 folks on my team. Okay, have a seat. You're not going to like this. Kristen, stand up. Kristen's on my team. And now Laura, stand up. Laura's on my team. Same or different? Same team. I chose them in different order, right? Have a seat. Thank you, ladies. So does the order in which I call on these people matter for my team? Makes no difference at all. So I'll write that out here, like actually being really explicit. I'll write, okay, we had Laura first, and then we had Kristen versus Kristen first, and then Laura. What's that? Oh, I'm sorry. I was going to ask you, and I said, no, I got this. Thank you. So what I do is I pick two specific people, two specific objects, and I just put them first and second, and then I swap them. And I think in doing that with specific people or objects in mind, it becomes clear whether it's the same thing or a completely different thing. In this case, it's the same team. So the order in which I called on them made no difference at all. And so if you follow the flow chart, maybe just have that kind of in front of you. So we said no to the, can you choose the object twice? So that put us on the right-hand branch. And then the order matters no. Was that the top one or the bottom one on that branch, if you're looking? That's the bottom one. So what do we use? We use combinations. Down there at the bottom, it is a combination. And so actually doing the calculation is going to be easy. It's the hard work is getting to that point, figuring out what you're supposed to use. So we'll put a big C. The first number I need is how many objects I have to choose from. We were making teams from the students in this room. Kristen says 17. Anybody else? Not me. I know when I'm bested. Oh, it's 16 without me? Oh, it was 16. Okay, 16.
Are you counting yourself?
Don't count me.
Oh, I meant he was counting everything.
So is it 16 or 17? Let's just call it 16. Okay. So 16 objects to choose from, 16 people to choose from. And how many was I picking for this team? 6. 16C6. That's the answer to this question. And on the calculator, somebody can do it. And again, I'll walk around and make sure everybody can do it later this period. What do we get? 8,000. Oh, all right. So just over 8,000 different dodgeball teams we could make. That's a lot. Okay, let's go to part B. We'll go over here to Haley. Okay, so anybody ever play roulette before? You guys know what it looks like? The big wheel that spins around, and then you put the ball and spin it the other way, and then the ball lands in one of the slots. And so there are a bunch of slots on this wheel. They're the numbers 1 through 36, alternating colors. I don't know which ones are black and which ones are red, but anyway, it alternates. It alternates, right? Yeah, okay. And then the 0 and the double 0 are green. Those are generally bad for everybody playing the game. So here are the possibilities, and we're going to ask the same exact questions. So I'm going to just abbreviate here. I'm just going to ask the first question, can we repeat? So one possibility for the first roll would be 2, right? The ball could land in that slot. And then on the second roll, could it land in the 2 again? Absolutely, could, right? Could land in any slot in any time. So can we repeat? Yes, we can. And so with the flow chart in front of you, does this put us to the left branch or the right-hand branch? This is the left. And actually, because we crossed off one of those boxes down there on the left, we don't even have to ask the follow-up question. The question is, does the order matter? I'll just ask it because those are always the 2 questions we're asking. But it turns out it hardly matters because we're skipping a certain kind of question. So we'll say order matters. And again, to decide, sometimes it's really tricky to decide the answer to that question. So to decide, I'll just pick a specific outcome, I'll put them first and second, and then I'll pick the same outcome reversed. So maybe on the first roll, you get a 36, and on the next roll, you get a 0. Imagine that happening in that order. Versus on the first roll getting what? So we did 36 on the first and 0 on the second, versus 0 the first time and 36 on the second. Same or different? It's different, right? I mean, getting a 36 on the first one is different from getting a 0 on the first one. So does the order matter? Yes, it does. But regardless, we're on the left-hand path. What do we have to use when we're on the left? We have to use a multiplication rule. Yeah, so let's think about what we're going to have to multiply. So how many possibilities are there for that first roll? Patty says 38. We buy it? It could be 1, it could be 2, it could be 3, it could be up to 36, or it could be 0, or it could be double 0. So how many possibilities? 38 possibilities. That's for the first roll, first spin. And then how many possibilities for the second one? Is it 38 or is it 37 now? It's 38. It could be anything. Could be the same number again. Don't get into the habit of thinking that every time we count, the numbers go down by 1. They only go down by 1 if possibilities are removed. But you could get the same number each time. The third roll, 38. And we multiply all that stuff together. It's 38 to the third, absolutely. So I'll write that here, and I'll encourage people to use it if they feel really comfortable with it. But for the most part, I would say just write them out, even if it's a little bit annoying. It's really easy to, instead of doing 38 times 38 times 38, if you don't write it, it's really easy to do 38 times 3, because we're doing 3 spins. 38 times 3 is not anywhere near the right answer. Stephanie, it's okay? All right, last one we'll do together. Part C, the number of possible games of tic-tac-toe. You guys have played this before. We're going to assume the tic-tac-toe board is going to get completely filled up as opposed to the game ending early with some empty spots in the board, okay? So let's assume the board gets completely filled up. So first we'll just write an example board here. Okay, so the first person, how many slots are available for them? 9. Okay, so the first person can go anywhere. I'm just going to put instead of putting an X or an O, I'm just going to put a 1 to say the first person went up there in that slot. Now how many choices for the second person? Now there are 8 possibilities. The second person can go there or anywhere else, but they can't take the first slot. And then the next person has how many choices? Now has 7, so maybe the first person goes there. But you see that the number of choices that they have available to them is dwindling. So we can ask about this repeat. Can you repeat the same spot more than once? No. Once that top middle spot is occupied, nobody else can take the top middle spot. So can you repeat? Nope. Does the order matter? Suppose that the first person picks that spot and the second person picks that spot. That's one possible start. Versus the first person picks this one and the second person picks that one. Same or different? Those are different. So does the order matter? They are different outcomes. The order in which we put things there makes a difference. That's a yes. Okay, so because of the first question, no repetition. Are we on the left or right branch? So that's the right branch where you're not allowed to repeat. The order in this case matters, top or bottom of that branch. That's the top. And if we're in the top one of that branch, what do we use? We use permutations. Okay, how many choices were there for the first person? Or how many slots were there available? There were 9. And I said, let's assume the whole board gets filled up. So how many slots are we going to pick ultimately when all is said and done? We're going to pick all 9 of them. Okay. There are 9 slots available to start. We're going to choose all of them in some order. And that's going to tell us what the results of this game are. So somebody with a calculator can give this to us. 362,880. Okay. So the first 9 is because there are 9 slots available, and we're going to choose all of them because I said we're assuming the board gets completely filled up. So we're not going to stop if X gets 3 in a row early. Okay, so the last thing I will show is here on this page. So there's a link there that you can check out. I'm going to pull it up right here. So this is the web page that you'll get to when you go to that link. This is supposed to be all 362,000 of the tic-tac-toe games. Now, I don't have enough resolution to zoom in. Like you could keep zooming in and see more and more boards, but there's not enough resolution on the screen. So let's go ahead and pick. So, so Danny, you're going to be the X. Which slot did you want? All right, so Danny says the middle, and so the middle is about to become an X, but can I just point out, I don't know if you can see this in the back of the room, but do you see, well, I guess you could see this, the big X in the middle of that middle one, versus if Danny had picked his middle left one, do you see the X in the middle left of this mini one? Okay, so Danny says the first one there. So Danny's got the X, and notice in all 9 of the other ones, what do you see is the same? The X in the middle. Danny's already reserved that spot, so nobody else is going to get that. The board's going to go from there. Let's go to Mike. Which one? All right, so Mike says top right. Notice there's a big O in the top right of that one versus the one right below it where there's a big O in the middle right of that one. Okay, so Mike says up there. So we currently have the first X and the next O. And you can see the detail has just come in, right? But all 362,000 of these were there from the beginning. We just had to have enough detail. Okay, now the reds mean that the game is going to end. So if we end up getting to a red one, then I think red is Danny wins. And I think we'll see some blues when Mike has a chance of winning. All right, Danny, what would you like? All right, so Danny says bottom right. Again, notice that in all these ones here in the bottom right, we're about to see another X in the bottom right. Again, it's real tiny. There's no way for people in the back of the room to see. But as we zoom in, we've got this board now. Mike has some blue possibilities, so if Mike can land on one of these blues, he'll win. If Danny lands on a red, she wins. A lot of times it ties. Go ahead, Mike. Good choice. So Mike is up here. We zoom in. Danny? Bottom middle is there. Mike? All right. So so that was one of the games played out, but again, well, there you go, 362,000. Now the truth is the number we just got, was it 362? That's not quite right because some of the games end early. This one didn't get to, the one we just played didn't fill up entirely, right? So I happened to look it up just so I could provide the answer to this one. It's this guy. I'll put it here in parentheses here, 255, 168. Turns out this is how many like actual games could happen. The game we just played finished early, so there's 255,000 of the real games, but if we had let Danny and Mike continue playing even after the game was over, we would have found more possibilities. So it would have been up to 362,000. Okay, we have about 13 minutes or so. Yep, so you guys right now are going to work with your neighbors. There's this big counting activity. Whatever you can't finish now, you're going to try to finish over the weekend, so do as much as you can now. There is an answer key a couple of pages down the road. And finally, we're going to distribute a few different ballots, so as you guys are working on the counting, you're just going to do 3 quick votes. So, so go ahead and start working and then fill out some ballots as they come to you.